Hi everyone. Welcome to our presentation. My name is Lukasz Pasek. Previously I was working in the companies like CD Projekt Red or Microsoft at the HoloLens Experience team.
Good afternoon everyone. My name is Alamparambil. I used to work at EA and Ubisoft, formerly as a game developer. Before joining Unity, I worked as a Unity developer for a few years in small mobile companies.
So we both are part of the XR team at Unity, the team made up out of approximately 30 people like us. We are mainly responsible for the AR and VR development at Unity, including AR Foundation architecture and the future development. Before we jump to the subject of our presentation today, let me ask you a question. How many of you have used AR Foundation before? I see some familiar faces from the presentation yesterday as well. So for those of you who don't know or haven't used AR Foundation before, when you write the code for multiple platforms, it's very difficult to support all of them. You want to write the code once and deploy it everywhere. So this is what we are trying to do with AR Foundation while developing AR apps. You write the code once and you deploy to every mobile AR platform available. So we spoke about AR Foundation before. Jimmy and team gave a talk about underlying architecture 6 months ago at Unite at GDC. A few months ago, we spoke about the rendering techniques for augmented reality apps. All of those videos are available online, and the links to those videos will be at the end of the presentation. But this is what we'll be talking today about. These are the features coming later this year. And Jimmy, let's start to talk about with 2D image tracking.
Thank you, Lucas. So 2D image tracking, what is it? I think you guys have all seen the stuff in the corridor where we use the Unite app to see an augmented picture on. That's basically what image tracking is. So the AR platform will detect a 2D image that exists in the world and will return the pose of that image back to you. And you can use that pose meaning the orientation and position of the image in world coordinates, so that you can use that pose to augment the reality of that environment by adding some virtual objects on top of it. So you can anchor your virtual objects to that. So let's see how we would expose this in AR Foundation. First of all, we need a way to tell the AR platform what image we want to detect. So we would create an image asset, and the image asset would be not just the picture, but also some other properties about the picture, for example, the physical dimensions in the world of the picture. And that asset will be an asset that lives in Unity. And you could basically pass that down to the AR platform. But usually when you want to detect images, it's not just one image, it's usually a set of images. So you want to create these image assets and add a set of them to a database. And that database is the one that's passed down to the AR platform. And then you could basically have multiple image databases for different parts of your app. And then as you need, you could just send down the specific database of pictures that you want to detect in that area. So when a session detects an image, it basically sends you an event back up in AR Foundation that says, hey, I've detected an image, and I want to tell you what the position and orientation of that image is. And also, when you move the image around, the position and orientation will update of that image pose as the event comes up, that the updated image comes up. So we want to have a look at how this could possibly be done in the editor. This is kind of like a prototype of what the editor interaction would look like, but here goes. Here goes. Here goes. Could you forward it? Okay. So this is a video of me working in the editor with a prototype of what it would look like. So I have these image assets, and they have a reference to an image as well as physical dimensions. And the image asset database is basically a bunch of these image assets put together. And I have an AR image manager on my AR session origin. And what that does is it's similar to the AR plane manager in the case that when you detect planes, it basically says, oh, these are the events these are the planes that have been detected, and these are the sizes, etc. and we can use that to actually render the planes. In the same way, when the images are detected, we would basically get an event that says, okay, these are the images that are detected, and this is the pose of that image, and then we can basically use a prefab to set on that place where the images are detected, and we could do other things with it as well. But in the simple case of just putting a prefab on, we have these axis prefab, the green, red, and blue axes, and we put that image, that axis on as a prefab on the image manager, so that it can basically be generated whenever a particular image is detected. So here's an example of that in action in an app. So I have a Unity logo as my image, and when it's detected, there's a prefab of this axes that are actually generated at the place, and as I turn the paper around, it moves around with it. So this is an example of 2D image tracking, and that's one of the new features. The next new feature we wanted to talk about, Lukasz, is 3D object tracking.
Yes, that's correct. But before we'll talk about the details, let me play you a video by one of our evangelists, Dan Miller.
Woo,
shout out to
Dan.
him, sits right in the middle. So he used the 3D object tracking to find the model in 3D space and place augmented visual objects around that real object in his scene, and then started the animation resulting in this video. So this is what you need for the 3D object tracking. So conceptually, the 3D object tracking is very similar to 2D image tracking, although you are trying to look for a different type of data in your 3D scene, in your 3D world. So to get that data, we will provide you a scanning app. So you will be able to scan a model. Once that model is being scanned, you will get an associated data with it. You add that data to an asset within the editor, put the asset into the collections of sets, and at this point you can give a set to the session to let the session know what type of objects should be detected during the runtime of the application. Every time when the object is being detected, added, or updated, you will get a 3D pose, and the 3D pose contains some information about the position and the rotation of the object in 3D space. And this is a sample demo. Dan's demo is so much better than that, so let's go to the next feature, face tracking.
Face tracking. So face tracking is a feature where the AR platform returns a pose for your face in terms of the device coordinates. So the front camera will face you, and then as you get these poses back, you can do things like augment your face and provide some interesting examples. So for example, the sloth face you see here. That's more on that later. But essentially, face tracking, how do we kind of expose this in AR Foundation? We want to get some events for when the face is added or updated. So when you detect a face for the first time, you get an added event. And as you move your face around, you get an updated event, which basically changes the face pose. And the face pose is the orientation and position, as I said before, from the camera, the device camera. We also get other information from the face, which is the face mesh. So if you imagine my face as a mesh, all the triangles over here, you get the vertices and the UVs that make up my face. And so you can use that to do things like occlude my face, so that if you have some 3D object that you, like let's say you have glasses that you're augmenting your face with, it doesn't show through on the other side of your face as you move around. That's one example. I'll show you another example just now. The vertices, UVs, and indices that you get from this will be pluggable into the Unity Mesh API. So you can just plug it into regular Unity Mesh in the editor, and that would help you to, along with a mesh renderer and a material, would allow you to see what the face looks like, for example. And some other information you get is the blend shapes from the face. So these blend shapes will return coefficients. So blend shapes are basically parts of the face that can provide information of what your expression looks like in a specific instance. So for example, if I've raised my eyebrows, there's blend shapes for each of my eyebrows that says it's raised up or it's lowered. So it'll give you coefficients that say, okay, if it's raised up, say the coefficient is 1. If it's lowered, it's 0. So a whole bunch of these different blend shapes I put on your face. There's 52 of them, and we can get those coefficients and plug them into a skin mesh renderer that has the same set of blend shapes. And so the skin mesh renderer does not necessarily have to have my face. It could be any face. So for example, the sloth face. So you put the sloth face and create these blend shapes and change the coefficients, and it'll basically create different expressions on the face of the sloth, which mirror the expressions on my face. So that's basically the setup that we have in AR Foundation. What does it look like in the editor? Again, this is a prototype of what it would look like. In the AR Session Origin, just like AR Plane Manager and AR Image Manager, we have AR Face Manager. And what does Face Manager do? It gives you the option to reference a face prefab. In this case, the face prefab just uses the pose of the face and puts in like those the axis prefab that we saw before for images. So what does this look like if we just set this up in the app? It would look like this. That's me moving around with this axis prefab following my every move. So as I look down, it moves its orientation and position. As I move around in the scene, it moves the position as well. What else can you do with this data? So you have a face manager. You could put a different prefab on it, and the different prefab might have, for example, a mesh visualizer. And the mesh visualizer basically takes the information that you get, like the vertices and the UVs, and you can set it on an empty mesh that's also in that game object. And that game object also contains a mesh renderer and a material. So now if we have all this set up together, what you can do is render a mask on your face, essentially, which is made up of your face mesh. So here's an example of that working. This was me recording myself during the World Cup. Croatia, go Croatia. Oh yeah, we're going to win. Oh, halftime. It's time to change teams. Hey, go France. Yeah. All right. So the other thing that we can do here with Face Manager is we have all these, another prefab, which is a skin mesh renderer. And the skin mesh renderer has the sloth skin mesh. And the sloth skin mesh is actually divided into blend shapes, the 52 blend shapes I was talking about before. And so we have this face feature visualizer, which basically takes all these coefficients from these blend shapes and plugs them into the skin mesh renderer blend shapes. And when you do that, it basically mimics the expressions on my face. So here's an example of that working in an app. There you go. Oops. There you go. Could you turn that on?
Yep.
Sorry. All right, that's me basically changing my expressions, smiling, raising my eyebrows, surprised, and the sloth basically does the same thing. It also has the face pose on it, so as I move my head around, it also follows my head. And that was face tracking. How about the camera image API? That's a new thing, right?
Yes, camera image API is a set of new functions. So allowing you to access the underlying AR background texture data. So up to this day, whenever you wanted to get an access to the pixel data of the AR background renderer, you had to do things like read the pixels, get the pixels, and usually they weren't the most efficient way to do so. So not designed to run every frame and allow you to do any image processing. With the camera image API, you basically can access the underlying texture through an API defined by the request you are providing to that API. The API itself is synchronous as well as asynchronous, so you have a choice of if you do not need to get the data within the same frame, you can do it asynchronously and process it later. So here we have an example code of what you can do with it. In the first block of the code, you ask the camera subsystem to get the latest image. Once that's ready, once that's succeeded, you specify the conversion parameters. The conversion parameters I will cover in a moment, but they will describe basically the type of data you will get out of your original image. We get the pointer to the texture we want to send the data to, and we convert that data. Once ready, we apply the data on the texture itself, so the data is being sent to the GPU, and it's ready to be rendered. So this is a very simple convention parameter set. It basically what it does, it takes the AR background renderer texture you see on the bottom right corner of the screen and gives you the texture you see on the top of the screen. So this is what you see is what you get. You can modify the parameters, so you can specify the transformation. So whenever you specify the transformation, you can flip it in X or Y axis, or you can combine these two together. You can do more than that. You can specify the output dimension. So it's worth mentioning the output dimension cannot be bigger than the original size of the texture. So you can't do upscaling, but you can downscale the texture. So it's very important if you do computer vision algorithms and you don't need to use the entire texture resolution. You can change the output format of the texture. So usually you get the texture in RGBA format. But if you do not care about other channels, you can specify a different texture format. In this case, it's 8-bit fixed size texture providing only red channel data. Or you can specify the input rectangle. So you can imagine a scenario where you are doing the face detection and you get a rectangle describing the position of the face in 2D space on the texture itself. So you can get that face information, that face part of the texture out of the original AR background renderer and display it on the screen. So here we have an example demo showing that feature in place. There's not much visible on the screen. There are actually spheres, 3D spheres floating in the space. They're not visible to you because when the player took the snapshot of the environment, projected that texture on the spheres itself. So they blended with the environment. Once the player steps aside, those spheres suddenly became visible. And this is the video how it works. So the main goal for the player is basically to find the original spot where the picture was taken from. And this is an example of how you can interact with an environment by using the texture data. In this case, once all the spheres are found, they naturally blend with the environment, giving that nice transition effect. As I have mentioned before, you can use it for computer vision algorithms. Here's an example using one of our assets available on Asset Store. One of the assets available on Asset Store.
It's not animating.
Using OpenCV. So that does the post-processing in real time. You still see there's a plane detection and the point detection happening in real time, as well as the post-processing on the top of it. So there's no stall. Everything happens really fast and allows you to do post-processing. There's another example here where we do multiple object detection based on the color of the object. So we try to categorize what we see on the screen. We look for blue objects, yellow objects, and red objects. And we do it in real time while the AR is still working in the background. And that's it for the camera image API. The next are environment probes.
Environment probes. So Unity already has a concept of reflection probes and light probes. Mainly we are looking at reflection probes here. So the picture there shows a reflection probe within a space station. And what it does is it takes an environment map of the space station so that it can do good image-based lighting on any virtual objects within that space station. In this case, the space station is a virtual level. But in the case of AR, you actually have a real environment. And the AR platform is going to return a reflection probe that looks like the environment around it. So it uses both the video feed as well as some machine learning techniques to figure out what the lighting in the scene would look like. And so it returns an environment cube map of that particular area which can be set on a reflection probe in Unity. And Unity already has the lighting workflow and everything so that if you set this reflection probe up properly, you can use any reflective material, standard material that will actually automatically use that. So all your virtual objects in that area would look very much as if it was lit properly and belonging to that particular real environment. So this is a powerful lighting solution that can help you make your augmented virtual objects look really good. Can we go to that? Okay, so this is how we would expose this in AR Foundation. We'd have a setting, first of all, to allow for either automatic or manual generation of these environment probes. Automatic means the AR platform will generate these environment probes in regular intervals around the real environment so that it can measure the lighting or show the image-based lighting in different areas. Manual is if you're focused on a specific area, you can say, I want the environment probe for this particular spot, and it'll generate an environment probe for that spot. And it will use kind of the video feed around that spot, as well as, as I mentioned before, the machine learning to figure out a good lighting model for that spot. I'll show you an example later how that looks like. For each of these environment probes, we'll get an event that says, well, the environment probe was added or update. So the added is when you first start getting these new environment probes in the scene, and the updated is could happen multiple times, usually after a few seconds, because it takes a while for the machine learning to figure out, oh, okay, I know now a better estimate of what the lighting looks like in this area. But also it has more information about the environment because you're probably moving around and it's seeing more of the environment. So it starts updating this as it gets more information. So after every few minutes or every few seconds, you'll start getting these updates that will update the cube map of the environment. So each of these updates contains the pose, essentially the position and orientation of that probe, the bounce extent, which is essentially how far you can go with your virtual objects around this and still have realistic looking lighting using this probe. And the last thing is the cube map, which gets updated, as I said. So you'd have a new cube map as a new event comes through. So how do we populate this in the editor? So this is an example of a prototype of how we would do this. Again, we go to the AR session origin and we add a script that basically is similar to the plane manager, etc. It will be called the AR environment probe manager. And the environment probe manager will have the ability to say, I want to automatically place these environment probes, or I want to manually place them. So the automatic placement will tell the AR platform to generate these environment probes. It also has a reference to an environment probe prefab. And these environment probe prefabs will receive the events from that we were talking about before, and you can do whatever you want with it. In this case, what we're going to do is the most basic thing you should do is basically stick the environment cube map that you get onto a reflection probe. So in this case, we are also putting a sphere with a reflective material on it so that we can visualize what this probe looks like in the world. So the sphere is just for visualizing. You don't really need the sphere. But the reflection probe is what is going to actually update the lighting in your scene. So you can use image-based lighting using just the reflection probe. So, but because we want to visualize it in the scene, we added that sphere and reflective material. So what does it look like in the app? This is what it looks like. I created that's the sphere that I was telling you about before. It's kind of visualizing what the reflection probe looks like because it's just a completely reflective sphere. So these are just a couple of reflection or environment probes that I placed in the scene. So that was environment probes. So what's up next, Lukasz?
Let's talk about tools. This slide may not look like much, but those three tools are here very important. Mock layer, remoting, and simulation. Let's start with the mock layer, which is a backend running under the AR foundation. So if you think about the mock backend here, it's a yellow block on that scheme. It works between the tool using it and the entire user's code, including AR foundation. So what it allows you to do is to alter the state of underlying AR data. You can modify any information AR Foundation stores underneath, including settings, plane data, points data, camera position, etc. For developers, it allows you to create test scenarios, mock the data for within the editor debugging purposes. For tools developers, you can create tools on the top of that mock backend, and you can be sure that if you base your tools on the top of AR Foundation, all of that functionality works out of the box for your workflow. Let's start with the first tool built on the top of that, which is remoting. Remoting is built from the two modules, the one running within the editor and one running on the mobile phone. So we provide you an app running on the mobile phone, and that app takes all the AR data, sends to the editor, and through the mock backend provides to the AR Foundation. So it has a support for everything AR Foundation currently supports, as well as the touch input, works over a cable and over Wi-Fi. And as you can see on the UI here, you specify the IP address of the device you want to connect to. You specify if you want to use the compression or not, as well as the downscale factor. Downscale factor will take the resolution of what's being rendered within the editor and send over to the mobile phone and scale it accordingly. So if your network bandwidth doesn't allow you to stream very fast, you can adjust it based on your needs. And you can see there's a record session button. I will cover that in a moment. And for now, let's see how it works currently in the editor. So when you have your AR Foundation app, you open the remoting window, and I'm using here a local host address because the phone is connected over the cable. Specify the camera you want to use to stream, start the app, and once app is running, I connect to the mobile phone, and there it is. I see the AR preview within the editor. All the data is being sent to the editor, so I can test the logic of my AR data immediately. There's no need to deploy to the device every time I do any changes. So here is an example of how it looks like both at the same time on the device and within the editor. So on the right, we see the same app running on the mobile phone, and this is being streamed from the editor to the mobile phone. So you can imagine a person running your game on a mobile phone, testing it, giving you a feedback, and you make changes according to the feedback immediately within the editor to adjust scene. Here I duplicated the robot, moved it around, and all of those changes are being visible on a mobile phone immediately. The next feature of remoting is recording. When you record a session, you essentially capture all of the data being sent from a mobile phone to the editor, and you can replay it at any time later in the future. So at this point, you can imagine a scenario where a QA gave you a remoting session being recorded and ask you to debug some particular issue with your app. That's what you use it for. There is no need for the mobile phone to be connected. In this case, I recorded a movement, saved it in a file, and when I'm ready to load it, I just tick the box next to the use recording option, and find the file I'm interested in about, and play. Once play is activated, the data coming from a mobile phone, if it is connected, is being ignored, and the recording session takes over the control. At any point, if you stop playing and the mobile phone is still connected, you are going back to the remote mode. In this case, I just found another file. I just wanted to see what I was doing back then when I was recording the session. Keep play, and it replays all the movement as well as the AR preview. So all the texture behind the robot, etc., is also being stored as a part of the file. The next option for you is to extend it. Since we share with you the app as well and the source code of the app, you can extend it yourself. So if you have any need for the AR data within your own workflow, you can consume it and add features to the app to extend it. In this case, we see one of the internal teams created a virtual camera production app on the top of the remoting. So they took the app, they've added a functionality like take a snapshot, start recording, change field of view, and they see what's being rendered within the editor, and they can guide, they can create cutscenes using the visual camera for a better feel. So if you'd like to start using it, it's already available. Here's a link to the tool, to the post describing how to get started. The link will be also available at the end of the presentation. If you have any feedback, the tool is still in the alpha, so any feedback is more than welcome, and we will make sure that any suggestion will be listened and try to make it better. Second tool built on the top of the mock backend is the simulation. So if you think about the mock backend being very close to the core, feeding the data directly to the underlying AR Foundation code, simulation layer is a more friendly, set of functions allowing you to inject the data from your own code running within the editor. So when using remoting, the data is coming from a mobile phone. When using simulation, the data is coming from your own script. So there is no need for the device to be connected to the editor at all. In this case, we programmatically create two planes and change their boundary points, and those planes interact with the user. Everything is still working. Those points floating in the background, these are the reference points you would see being detected on your mobile phone. They're also being simulated here. In a very base scenario, how it could be used, it's a script injecting the data to the AR Foundation. Here is a script that takes the box, takes its size and position in space as well as the rotation, and based on that, update a virtual AR plane in your editor. So any code interacting with the AR data will consider that block to be a virtual AR plane. So that's it for tools. Let's go to the next subject, which is LWRP support.
LWRP. So I don't know, how many of you have worked with LWRP? Oh, I see quite a few hands. So essentially, if you think about scriptable render pipelines. So scriptable render pipelines are the new way of doing things for custom control of how Unity handles the different stages of rendering. So having it scriptable means that you're able to customize each and every stage of the rendering. But in most cases, people don't want all the freedom in the world. They want to have a default set of a default pipeline that they can run that gives them pretty good rendering effects. So to do that, basically we have two default rendering pipelines. One is the HDRP, which is more suitable for higher end consoles, etc. And the other is LWRP, which is pretty good for mobile and lower power devices, exactly. So basically, if you look at the picture there, that's an example of LWRP running on a mobile and giving you pretty good rendering effects. The essence of it is LWRP gives you a very optimal way of rendering on mobile with pretty much a whole plethora of new kinds of shaders, etc. So why is it exciting for us? Because in AR Foundation, we use the mobile platform, and we want to kind of make it very, like all the virtual objects that we create in the real world, we want them to look very realistic, and we want to have all the power of all the amazing shaders that LWRP supports. So this is good. Since we introduced LWRP support in AR Foundation, you can use all this power right out of the bat. So can we go to okay. So this is basically the features that we have in LWRP that helps us make much better AR Foundation apps, essentially. So you get really optimal single pass forward rendering. You get the standard PBR materials, which make your virtual objects look really good. You also get the standard non-PBR materials. But I think the most important or most interesting for us in LWRP is the ability to use shader graph. So what is shader graph? Shader graph is a node-based editor that you can use to create a shader without writing code. So essentially, the node-based editor allows you to see at each stage what the shader would look like at that stage. And also, obviously, at the final stage, you'll be able to see what the actual shader would look like just in the preview. But more importantly, you can basically iterate on the shader and be able to figure out, okay, if we wanted to do this, this particular effect, how would I start doing that? And if I wanted to alter it in a little fashion, how would I change a particular node to give me that effect? So in effect, it gets you the iteration of being able to iterate through shaders and be able to get better looking shaders really fast. Of course, you might need to optimize it later, but it makes the prototyping of shaders much easier. So here's an example shader that we see here, which Dan Miller had nothing to do with. So and here is what it looks like. Oops, in the scene. Can you animate that, please?
One more.
There you go. So that's that shader that we saw in the shader graph applied onto a plane on the floor, on the 5th floor of Unity San Francisco, and you can see the checkerboard kind of flowing into. So there's a vertex deformation on the shader, and all that stuff is, I mean, it's just straight out of that shader graph. So this is exciting for us. We're just excited to see what kind of shaders people come up with that we can see in AR. So that's basically all the stuff we wanted to talk about. We basically went like a whirlwind tour of all the new features, most of the new features, and workflows. So we'll basically, anything else to talk?
Yep, we are really excited to see what you will come up with once you put all of those features together. If you have any questions, you can ask now, or we will be waiting outside of the room in the QA section. There are the links to the previous two presentations we've made, as well as the remoting tool and our contact details if you want to ask us a question after the conference. Thank you.
Thank you.
Hi there. Can you clarify which of the features you've shown here are available today and which are yet to come? Okay. But you said
the title of the talk is A Look Ahead.
You said the remoting is available today.
Oh, remoting it is available
It's
today.
in preview, yes.
Yeah.
There are certain features that are available in preview today, but most of them are coming up.
Yeah, I had a question about the face tracking system.
Yes.
I was wondering if you could generate like a unique ID to identify a person using the face tracking system?
There is an ID that's returned that is a unique ID, but it will not be.
I mean, let's say you had an app to like scan your face.
Right.
Okay, give me an ID, and then could that be anytime you look at someone's face, you'd realize that it's them?
It's not. It's only for that particular session that it's unique.
Got it.
So it can't.
Not between sessions.
Not between sessions.
Got it.
Oh, beautiful. Thank you. My name's Lex, White Label AR. I'm a Unity dev. I'm so grateful for everything you give us as developers. And I know right now the tool set has a shadow texture that allows you to overlay shadows in the real world. And in terms of performance in the future, do you see anything in terms of blob shadows, any other kind of tools that we might be using as a best practice, or what do you think about, I think, shadows, and what other tips do you think of rendering something accurately in AR that looks compelling?
So we actually gave a presentation a few months ago. So one of the links goes to rendering techniques in for augmented reality apps. So that's where we spoke about what you can do to make the apps more immersive. In terms of performance, we are working over the best practices to talk about when creating AR apps.
Beautiful. Yeah, I did see that talk. Thank you so much for all of this. Looking forward to the future. Thank you.
Welcome.
Hey, first a shout out for the environment probe stuff. Nobody else clapped, but I thought I should have. It was really, really cool.
Thank you, thank you. I had nothing to do with it though.
I had more questions about the face tracking stuff. Is that only iPhone X based, or is that like
Whichever
OpenCV
AR
based?
platform supports face tracking will be supported.
All right. And can you be using multiple cameras at the same time? So one is doing facial tracking while the other one's piping data in from the.
If the AR platform supports it, actually currently we only allow either face tracking or world tracking. So there's not, we can't do both at the same time.
But would I be able to get both camera streams? So even though we're only tracking my face with the front, the rear, whatever, the one that's tracking your face, can I still get the video stream from the other camera?
That is, I am unsure whether you'll be able to. Like, it would have to be a special call. Yeah, it's not the intended workflow, but I mean, it's possibly something we could look at. But I don't think it's something that would be default supported.
Thank you.
Yes.
I have two quick questions. The first one is about 3D tracking. How do you get the information on the 3D object? Do you have a scan process, or do you require a CAD file?
Yes, so we will provide an app you will use to scan the model you want to track later during the runtime. So you will use that app to collect the data, and then you use that data when creating the app.
And second one is about about multiplayer. Do you support multiplayer?
What is multiplayer?
I mean, two persons can communicate with each other, like the AR chess.
So, I mean, that's kind of independent of AR, right? Is that what you're talking? What are you talking about? Is he talking about like?
Like if I put a virtual object on the floor,
Right.
you're able to see that object.
I would
Right.
say
That's currently. I mean, it's currently in the pipeline, but it's not something we talked about. But yeah, it is currently in the pipeline.
So
We do plan on doing something.
stay
about it.
tuned. We will be making more announcements in the close future.
Thank you.
Welcome.
Hey, I got a couple of questions for you. So face tracking. Are there going to be like event listeners for the different expressions, like is smiling, or mouth open, or do we have to do like math to figure that out?
No. So basically, what happens is you get an event update whenever your expression changes, but also like usually you would get an event update every frame because your face is always moving, right? In conjunction with it. But even if your face was completely still and you just moved your expression, that would actually generate an event. And the event will have a full list of all the blend shape coefficients. So you'd basically say, oh, this coefficient has changed from 0 to 1. So for example, if you have a mouth open coefficient, you can say detect the mouth open coefficient, and you get an event for face updated. Check the mouth open coefficient and see if it's turned from 0 to 1 or whatever value it is. If it's a threshold that you want to be above, and I say, okay, that's what I need to detect.
Okay, so is it like specifically mouth open 0, 1? Like is there like a list of those?
There is a list of them. There's a list of 50 different blend shapes coefficients. I can send you a list, essentially.
Oh, okay.
But it's a good feedback. We could think about trying to make it easier to detect.
Yeah,
Right.
I've been doing a lot of work with AR Studio, which is like Facebook's face tracker thing, and they actually have a very simple list of events that you can listen for, like mouth open, eyebrow up, and then you can trigger different animations and things like that with it. So it's something to think about. If it's
Yeah,
really hard to
totally.
work
Yeah,
out, that'd
sounds
be
like.
great. And then, does it support multiple faces? Can you have like 2 or 3 people having face tracking at the same time?
It should work.
You would just set up,
If the platform supports it, yeah.
Okay. And for the face mesh, will you be providing like a PSD template? Because usually it's like stretched out when you have like, if you're trying to make your own little face mesh, it'd be real helpful if there was like a PSD template.
So what you get with the face mesh is actually, so you'll get your face. I mean, you'd get the vertices, UVs, and I guess the indices of the vertices for your mesh. Then you'd just get that, and you could basically save it onto a Unity mesh, and you could save that out if you wanted. But what you're talking about is basically the texture coordinates?
Yeah, no, I mean like, so if you're like importing like a, you know, you want to make like a clown face or something that gets put on somebody's face. I assume that would be like some image that you import and assign it to the mesh and it gets applied, correct?
Correct, yes.
Works? So I was just wondering if there's a template for making, because usually it's like
there is not, because there's two reasons for that. One, well, we could actually do that, and that's actually a good suggestion. We could take that back, but there is also slightly different variations of where the UVs are based on different faces, right?
Yeah.
So you have to kind of compensate for those kind of things.
Okay, and then, environment probe thing?
Yeah.
Does that also, would you get lighting direction from that so that like shadows can match where the light source is coming from?
Sort of. It's basically just a cube map, so like an environment map essentially, and you can decide that it's brighter from this side, therefore the lighting is coming from this side. So it doesn't give you just a direction out of the box, but you can decipher it from what that. It's basically meant to be used as for image-based lighting, not to actually determine the shadow direction or anything, but you could do that, yes.
Okay, cool. And then my last question, and I'll leave you guys alone. The image detection, how flexible is it with the physical size? Like if I just wanted to like have one app and I could detect an image if it's little or big.
That's dependent on the AR platform. So depending on the platform, we might have to do either, you have to specify the size or not.
So unfortunately, we need
right,
to
like
finish
we,
now.
we can, certain AR platforms allow you to do without actually specifying a size, and others need the size. And actually it might change as well, so depending on like what the AR platform comes up with next, right?
Cool.
Thank you, and that's all the time we have for. Thank you.
Thank you.
And if you have more questions, we'll be outside. Thanks, guys.